All right, let's talk about a problem that I'm sure you've run into. You've got a list of numbers, and you need to get sums of different parts of it over and over again. But the numbers also keep changing. Your first simple solution works, but it's slow. Today, we're going to pull back the curtain on a really clever data structure called the Fenwick Tree, or as some call it, the binary indexed tree. It solves this exact problem with a kind of elegance that's just, well, it's pretty amazing.
So here's the game plan. We're going to start with the problem itself, why this simple approach bogs down. Then we'll introduce our hero, the Fenwick Tree. After that comes the fun part. We'll uncover the binary magic that makes it so fast. We'll see it in action, and finally, we'll talk about when this should be your new secret weapon.
Okay, let's get right into it. We're going to start with a situation that I guarantee feels familiar to anyone who's ever written code.
So just imagine you have some numbers. Nothing fancy, just a plain old list. And for this entire explainer, let's just keep this simple array in our heads. 1, 3, 5, 7, and 9. This will help us see exactly how everything works without getting lost in big numbers.
Now, here's where things get tricky. Imagine you're getting hit with a constant stream of two kinds of requests. First, hey, what's the sum from this index to that index? And then right after, okay, now change the number at this other index. And this happens thousands, maybe millions of times. You can probably see the problem here. If you just loop through the array every single time someone asks for a sum, you're going to have a bad time. The program just grinds to a halt. We clearly need a smarter way to do this. And this is where we stop thinking about brute force and start thinking about elegance. So let's meet our cleverer data structure, the Fenwick Tree. So what is this thing really? At its heart, a Fenwick tree is just a sneaky way of pre-calculating and storing sums. It doesn't store the original numbers directly. Instead, it stores information about the numbers, which lets us do our updates and our sum queries way, way faster. It's a total specialist. You know, it's not a jack of all trades. It's designed to be absolutely brilliant at these three things: getting the sum from the very beginning to any point, using that to quickly find the sum of any range, and changing a single value without having to recalculate everything from scratch. So if we put it head-to-head with a regular array, you see the trade-off. Yeah, you use a tiny bit more memory, but in return, you get this massive boost in speed. And here's the kicker. It's a whole lot easier to code than other complex structures, like segment trees, that try to solve similar problems.
Okay, so how does it work? How does it get that speed? Well, the name binary index tree is a huge clue. The entire secret, the whole magic trick, is all about binary numbers. Okay, you ready? This is the secret sauce. In a Fenwick tree, the value at, say, index 6, doesn't just represent one number. It represents the sum of a range of numbers. And how big is that range? That's the beautiful part. It's determined by a property of the index itself, something called its least significant bit. The least significant bit, or LSB, is just a fancy way of saying the value of the rightmost one in a number's binary form. So for the number 6, which is 110 in binary, the rightmost one is in the 2's place. So its LSB is 2. And we can find this with a really cool bitwise trick that our computers can do almost instantly. And this is the part that's just so cool. That whole logical process we just walked through, it all gets boiled down to this one single beautiful line of code. It's this tiny little operation that powers the entire data structure. All right, so we have our magic LSB trick. Now let's see how this little piece of binary wizardry actually powers our two main jobs: updating a value and asking for a sum. So when we update a value at some index, we don't just change that one spot in our tree. We also have to update all the other ranges that include that spot. Think of it like a chain of parents. And how do we find the next parent in the chain? Simple. We just add the LSB to the current index. We just keep jumping up the tree. And when you look at the code, you can see that logic perfectly. We have a simple loop. Inside, we add our value. And then there's the magic jump. IDX plus equals IDX and negative IDX. That's our LSB trick, moving us to the next parent. And that's it. It's so unbelievably concise. Now, getting the sum is pretty much the same idea, but in reverse. To get the sum up to a certain index, we start there and grab its value. Then we jump backwards by its LSB to find the next chunk of the sum. We grab that value, and we keep jumping back, collecting pieces of the sum until we get all the way to the beginning. And once again, the code is a perfect mirror of that logic. We start a sum at 0, then we loop, We add the value from our tree, and then we take that backward jump by subtracting the LSB. It's just beautiful, isn't it? Both of the core things we need to do are just these tiny, super fast loops.
Okay, so we've seen the mechanics, we've seen the binary magic. Now for the most important question. When do you actually pull this thing out of your toolbox?
You'll often hear the Fenwick tree compared to its bigger, more complicated cousin, the segment tree. The key difference is that the Fenwick tree is a specialist. It's not as flexible. It's really just for sums and single-point updates. But the trade-off is huge. It's way simpler to write, it uses less memory, and for the jobs it's good at, it's often even faster.
So here's the bottom line. If your problem boils down to needing lots of sums over ranges and you only ever change one value at a time, the Fenwick tree is your new best friend. It's fast, it's light, it's easy to code, which is why you see it all the time in places like competitive programming where every second and every byte counts.
And this isn't just for coding challenges. This stuff is used out in the wild. Think about a leaderboard in a game that needs to update scores constantly, or a financial system that needs running totals calculated in a flash. Anywhere you need those dynamic prefix sums, the Fenwick tree is a serious contender. You know, when you step back, the Fenwick tree is just an incredible example of how a really deep understanding of something simple, in this case just how binary numbers work, can lead to these powerful, efficient solutions to big problems. It just makes you wonder, right? What other amazing solutions are out there, hiding in plain sight, built on top of one simple, clever idea?